All right, we've looked at voltages in a Y system. Now we're going to look at currents in a straightforward Y connected system. When you calculate currents in a Y system, you'll see that the loads, the three Y connected loads we have, are all connected in a phase. Load A is connected across A to N for a voltage. Load B is connected across B to N for a voltage. Load C is connected across C to N for a voltage. So the loads always see phase voltage. Phase voltage for this system is always the lower voltage of the two. So our voltage across each load is 120 volts. If we know the voltage and the resistance or impedance that we have in each phase, we can find the current in each phase. Phase current IA to N equals phase voltage VA to N divided by the resistance, I guess you'd say RA to N. So 120 volts divided by 15 ohms will equal 8 amps. So that is the phase voltage in phase A to N. In phase B to N, we have the same voltage and the same impedance, so we'll have the same current. IB to N will equal 120 volts divided by 15 ohms, which is 8 amps. Phase C to N is 120 volts and 15 ohms as well. So the current for C to N is 120 volts divided by 15 ohms. Again, 8 amps. So our three phase currents are each 8 amps. Now, to compare the phase current to the line current, a way to think of it is, if I wanted to measure the line current feeding this three-phase system, I could put an ammeter in line A right here, connect it right in phase, and measure the line current. To measure the phase current, I would want to be right in the phase, so I'd put that ammeter, say, right here. I'd connect my ammeter right in the phase. Now, this load draws a current from the line through the load to the neutral. And there's only one path for current to flow from the line wire through the load in the phase to the neutral. If there's only one path for current to flow, the phase current that is here is exactly the same as the line current I would measure here. These two ammeters would read exactly the same current, and so we can say that I line equals I phase. That is rule number 3 for three-phase systems, is the line current equals the phase current. Those are about the only 3 rules we use for Y systems. And this is rule 3. Okay, now that we know the currents in this Y system, we're going to put the currents and the voltages together on a phasor diagram to show everything for this system. I'll start with the voltages, and again, the phase voltages are always in the same place. Phase voltage VA to N is at 0 degrees on my phasor diagram. Phase voltage B to N lags A to N by 120 degrees. So phase voltage B to N is at 240 degrees. And phase voltage C to N lags B to N by 120 degrees. Phase voltage C to N is at 120 degrees. Those are our phase voltages. We won't put the line voltages on this phasor diagram because it just clutters it up a bit. We know the line voltages lead the phase voltages by 30 degrees. We want to see where the currents go. So for me to put the currents on here, we know that the current in each phase is 8 amps, and we know that the line current and the phase current are the same value. The phase or line currents, we generally refer to them as line currents, but they're the same thing as the phase currents. To put them on our phasor diagram, the one thing we need to look at is what our power factor is. For these three loads, it says the power factor is 0.866 lag, which means the currents lag the voltage by a certain angle. So in your calculator, if we want to know what the angle is for a cosine of 0.866, we need to go second function, cosine on our calculator of 0.866 will give us an angle of 30 degrees. So that tells us that the current lags the voltage by 30 degrees. So for phase A to N, if this is the phase voltage here, the current is going to lag the voltage by 30 degrees. So that means my current of 8 amps is going to lag my voltage by 30 degrees. So IA is at 330 degrees, lagging by 30 degrees, and it is 8 amps. For phase B to N, it has the same power factor. So the current is going to lag the voltage by 30 degrees in phase B to N. So 240 minus 30 is 210. So I'm going to put IB is 8 amps as well at 210 degrees. So that is phase or line B current is at 210 degrees. And for phase C, it has a 0.866 power factor as well, which means in phase C, the current lags the voltage again by 30 degrees. So if the phase voltage is here, the phase current will be behind by 30 degrees. IC is at 90 degrees. It is 8 amps. So these are the three phase currents. This phasor diagram now shows the relationship between the voltage of each phase and the current of each phase. So for each load, in the load for phase A to N, that load, the voltage across that load is happening at 0 degrees. The current through that load is lagging that voltage by 30 degrees. So the current is behind the voltage by 30 degrees. We have the same thing for phase B to N and for phase C to N. The same relationship exists between current and voltage. The current lags the voltage by 30 degrees. Where the current is equal in each phase, which we have here, the current is 8 amps in each phase, and the current lags the voltage by the same angle in each phase, or the phase angle of 30 degrees is the same for each phase, we call it a balanced load. We always have to have two things to have a balanced load: the same current in each phase and the same power factor or phase angle in each phase. And that is all that we would find for that system. The phase voltages, plot them on the phasor diagram. The phase currents, put them on the phasor diagram. And that is really all we can show for a balanced load. In an unbalanced system, the phase current is not the same in each phase, or the phase power factor is not the same in each phase. And as soon as we have an unbalanced Y-connected load, then once we have done this same phasor diagram, there's one more calculation that we can do to find the current that the neutral carries. And our next video we'll go through an unbalanced load and how you calculate that neutral current. That's it for now.